All right, this is Algebraic Reasoning, Chapter 1, Section 1, Arithmetic and Geometric Sequences. In the core vocabulary that we're going to be talking about today, we're always going to start these off with the vocabulary for the day. And for this one, arithmetic sequences, we're going to define it as a sequence that has a constant difference between successive terms. Terms. Okay, it's basically a sequence that has constant difference between successive terms. So basically, let's say I had this sequence right here: 11, then a 15, then a 19, and a 23, a 27. That's a horrible 23. 23, 27, and a 31. Hopefully, you'll notice real quick that if I look at the difference. If I do 15 minus 11, I get an answer of 4. If I do 19 minus 5, I get a difference of 4. 23 minus 9 is 4. And if you keep on going, these are all 4 units apart. Therefore, this is arithmetic because it has a constant difference. Now, it doesn't have to go up. It can go down. These could all be negative 4s instead. In this case, they're not, but it's just a constant difference. It's either adding or subtracting the same number. Okay, a geometric series is very similar to an arithmetic series, but a geometric series is, or geometric sequence, I'm sorry, is a sequence that has a constant ratio. It's constant ratio between consecutive terms. Alright, and ratio is just a fancy word for the same thing multiplied or divided, okay? That's what we mean by ratio. So for a geometric sequence, let's say we have 2 pennies, 0.02. If we multiply that by 2, we get 4 pennies. We multiply that by 2, we get 8 pennies. Multiply by that 2, we'll get 16 pennies. Then 32 pennies. And before you notice how it's getting bigger faster, and then we'll get 64. Then we'll get $1.28, so on and so forth. As we get bigger and bigger, it'll start going. So each one of these, the common ratio is we are multiplying by 2. That's times 2, times 2, times 2, times 2. It has a common ratio. Okay. Now, a common ratio, which we just defined kind of for you, but just to give you kind of a more formal definition, a common ratio is the multiplier in, let's try that again, multiplyer in a geometric series or sequence. Between consecutive terms. And what we mean by consecutive terms, I didn't explain that. Like by consecutive terms, I mean like the first one to the second one to the third one, like this one to this one, this one to this one, this one to this one, this one to this one. That's what I mean by consecutive terms. And so the common ratio for this example that we just gave is actually times 2. That will be the common ratio. And it doesn't have to be multiplying. It can be divided by something. So a common ratio can be a third, multiply by a 3, or divide by 3. Those are both common ratios. All right, you can use those as a ratio. Let's scroll down a little bit. All right, last two words. Recursive rule is a formula. Oh, let's scroll a little bit better. Is a formula that uses the previous value, OUS, the previous term value, to define, D-F-I-N-E, the next term in the sequence, in a sequence. Okay? It has two parts. The first part is the first term. Oh, that's horrible. T-E-R-M in a series. And the second part is the difference or ratio between terms. All right, and so here's what I mean by that. So it's basically this formula that says, hey, step 1 is this. To get to step 2, you do this. To get to step 3, you start at 2 and do this. So to go at that previous example, let's say where we had, let me write that back up real quick. We had 11, then 15, then 19, then 23, 27, 31. Basically, what we have to have is we have to have two pieces. We have to have something that says, let's say, x of 1 equals 11. Now, if you see a subscript in math, that little 1 down there, that's telling you what x are we talking about. That means this x is a specific one of those. All right? In this case, because it has a 1, that means it is the first one. It's the 11. So we have to have two parts. One, what is the first term? So we just find it as 11. The other part, x of n, x of any given number, x of whatever x we're looking for, we do x of n minus 1 plus 4. All right? Now again, these are subscripts, and we'll talk about more of these as we go along. All right? Basically what this is if I have, let's say if I want x of 3. Okay? So I take x of n minus 1. Well, what's 3 at minus 1? That's 2. And I add 4 to it. So x of 3 equals, we know x of 2 is 19, or no, not 19, 15. X of 2 is 15 plus 4. Therefore, x of 3, the third x in the sequence, is 19. Okay, that's how that works. That's how a recursive rule works, and you'll get used to that as we go. But that's just the first. That's just kind of setting the groundwork. An explicit rule. Now, explicit rules you're a little more familiar with. Explicit rule is a formula that determines NES the nth term, so which nth, and by what I mean by nth is any term we're looking for, whether it be the first term, the 9th term, the 15th term. So the nth term by using the term number, okay? So an explicit rule, we'll use this same pattern. We'll stick to the pattern we just gave. An explicit rule would say something like this. For any given n, any given x, for whatever x I want, okay, I take that number, the actual n itself, and in this case, I'm going to multiply it by 4 and add 11. You may recognize it. This is very much like a y equals 4x plus 11. Y equals mx plus b. That is an explicit rule. And so, like, if I want to know the third term, instead of using this formula like I did over there, I can literally plug in 3 for x. So y equals 4 times 3 plus 11. 4 plus 3 is 12. 12 plus 11. 4 times 3 is 12. Oh, I put it up there wrong. It's not 11. 6. This should be 7. Be 7. Let me adjust my notes. 12 plus 7 is 19. And that would be, sorry about that, but this is the explicit rule for that formula up there. All right? And there we go.